done.
If you don't get it done, yeah. It's a simulation on the computer, so it's not horrible. All right, so our next section is going to be on electrons. And it's truly like what we were looking at last chapter was a lot with the nucleus, especially with like the nuclear chemistry, and that was what was changing. So dig into your, past the 5.1, you're going to start into a section that says notes there. Do you see it? And that's where we're at right now. So what we were looking at with the nuclear chemistry was the nucleus primarily. We deviate now and start looking at electrons. And it's really the electrons, for the most part, that give the element, like the reason why it bonds with things, the reason how it bonds with things. And all of that kind of dynamic is driven from the electron. So we're gonna focus in on the electron really tight, and then we're gonna look and we expand, and then we look at bonding in the next like few chapters. So we look at the electrons, we look at trends and properties, and most of those trends and properties are driven by the electrons. Then our next two chapters after that, 7 and 8, deal with bonding, different types of bonding. Then we get to chapter 9, and that's reactions. So how do we go through reactions, balancing equations, that sort of thing. And then that takes us right up to the semester divide. And then we get into working with those equations and how, you know, mathy kind of stuff with the equations. So that just kind of gives you a quick overview of what we're doing for the rest of the semester. But it's the electrons that are going to drive most of that. So that's why we focus so much time in on those. So if you think about like a flame, and we're going to do a lab on this, I think next week, if you look at your schedule, I think it's next week that we do the flame test lab. That flame test lab then will show you different colors for emitted light. Thank you, dear. Yep. And you can kind of think of that like fireworks. Okay, fireworks aren't just one color, they're a whole bunch of different colors, and that's all driven by the types of elements that are in the different fireworks and what light they give off. And it's the metals typically that are going to give you the different colors for those emitted lights. That's typically what they change up in the fireworks, and that's what we're going to change up in your flame test labs. So the emitted light is going to reveal the element's chemical behavior and show kind of the arrangement of those electrons. And we'll talk about that as we move through here. So light is a wave, and it's a form of what's called electromagnetic radiation. Is there stuff for you guys to fill in? Am I going too fast?
Like one word, please.
Okay, so I need to let you fill that in, and then we'll talk about it. So it's a wave, and it travels through space. Visible light is part of that. So if we look at the electromagnetic spectrum, this is what that spectrum looks like. And you have down at one end, you've got radio waves. And you guys are kind of familiar with radio and having a radio in your car. You may have them at home. But they transmit different waves, and your radio is designed to pick up those wave frequencies and then transmit it as sound. Microwaves are another type. So your microwave oven emits microwaves. Your phone also transmits, most phones, cell phones, transmit signals via microwave. These are pretty low amounts of radiation that they are sending across, so your body can handle that. Although your microwave oven is pretty intense, so if you were like inside there, you'd have problems, but you're not inside it. And they have a little screen that's on your microwave oven. You'll notice every microwave oven has a screen over the window. The holes on there are designed so that it won't allow this frequency of light, or the wave, the height of the light, or the not light, but the height, the amplitude of the wave for the microwave that's generated. It won't allow that wave to get out of there, because that hole is small enough that the wave can't get through that screen. Okay, and then you're protected on the other sides by the kind of the cage of the microwave. What those microwaves do is they will cause the food inside there, the molecules, to vibrate back and forth, and that vibration, then the water molecules inside them will, then the vibration generates heat, and that's how it heats your food up. Infrared then is heat, and they've got like, we can't see this, but they do have special cameras where you can use like an infrared camera to be able to view different things. They do that for like, well, hunting and warfare and stuff like that. They also do it for more practical purposes, like fire departments will use them to try to find people inside burning buildings. You know, it's too smoky to be able to see through. They use it in industry like construction to make sure that there's no leaks in things. And like, for example, if we had a pipe above the ceiling and there wasn't air getting to like one of the vents, they could hold that up and see, okay, yeah, there's a break in the pipe up there, and the heat is getting dispersed across the ceiling instead of actually getting to the vent. And they'd be able to use an infrared camera to kind of detect that. And they do it in lots of different applications in the construction industry. So that's kind of interesting. Then we have visible light. This is what our eyes can detect. So this stuff is all around us. Our eyes just can't pick it up. But this is what our eyes can pick up. You do have some critters out there that can see this, and you've got some out there that can see this. We're just not one of those critters. Anything, and then you can take the visible light, you can break it up by using a prism, and you can see kind of the rainbow here. So you've got your red down here, which is a longer wavelength, and then you've got your violet over here, which is your shorter wavelength, higher frequency. Then you get into the ultraviolet, and our eyes can't see this. But again, they've got special lenses and stuff that they can detect it. X-ray and then gamma ray. And these at this end are called ionizing radiation, because they're actually going to cause ions to form when they shouldn't. And that's what leads to like your cancers and issues like that. The UV radiation, then you can stop that with sunscreen. X-ray, they put like that lead apron on you if you go in for like X-rays. And then gamma rays, you need like several inches of lead. So it's some serious stuff to try to stop that. We talked about that last chapter. So these things down here can be really harmful. These things can too if they are intense enough. Like I said, if you got stuck inside a microwave oven, there'd be problems. If you get too much heat, there are problems. Our bodies are designed to be able to handle a certain amount of these. And some people can do it better than others. I can be outside for an hour or so and not really have problems. My husband's outside for like 10 minutes and he's burnt to a crisp. Okay. So it's just different people's bodies can handle a little bit more than other people. And you can handle a certain amount of X-rays. That's why you can have a certain amount done in a year. Gamma, you can handle a little bit of it. In fact, you're getting some gamma radiation right now. There's gamma radiation from the bricks in the wall, from the soil. If you have a basement in your house, the soil from your basement is emitting a certain amount of gamma all the time. But our bodies can handle a little bit of that. Okay? It's the intensity and how much. We can handle a lot more radio waves than we have gamma rays. But we can handle all of these at any point in time, just not much, especially on this end. Okay? So, properties of waves. All magnetic waves travel at 3 × 10⁸ meters per second in a vacuum. Now, luckily, all of our problems are going to be done assuming we're in a vacuum. Okay? So this will be the standard amount. And even if you go on to take AP Chem, that's the same thing. It's when you get into other places that's different. But the speed of light changes as it goes through different mediums. So for example, have you ever looked down into a pool and it looks like it's shallower than it actually, or yeah, shallower than it actually is? You know, it's that depth perception. It's weird. Or have you ever seen, let me see if I can find. Have you ever seen a pencil in a glass of water? You end up, the pencil looks like it's broken, even though it's not. Okay, that's because out at this, in this area here where we're in a gas, light is traveling at one speed. When it hits that water, it slows down and is traveling at a slower speed. And so that's why the pencil looks like it's broken, even though it's not. Okay, and that has to do with the speed of light. But like I said, all of the problems that we're going to do in here are assuming that we're in a vacuum, and that makes life easier. So we have an equation. C is this speed of light. That equals C. This is wavelength, and this is frequency. The speed of light, wavelength, frequency. So if your speed of light is held constant, which we said it's going to be, and I increase, I make my wavelength longer. Okay, so my wavelength is a bigger number. What's going to happen to this guy? Okay, and vice versa. So here, if we have our wavelength is longer, does that make sense? Wavelength's longer. Long wavelength equals low frequency. Yeah. Long wavelength, low frequency. Yep, that makes sense. So long wavelength is going to give us a low frequency. And then a shorter wavelength, smaller wavelength, will give us a higher frequency. And that's why this stuff is so dangerous, because it's hitting you more frequently, more rapidly. So you're getting more and more energy at this end being delivered versus this end. So that's why this stuff is so much more dangerous. All right, we're going to do problems next week using that equation. This C might be familiar to you. It's part of a very famous equation. Anybody remember that famous equation? Yeah? Yep. E equals mc squared. And that's the same C that appears in that equation. It's the speed of light. And that's energy equals mass times the speed of light squared. And that talks about the energy that it can be contained in the mass of the nucleus of an atom. And that's the energy that's released when you change some of that mass into energy. And that's that nuclear kind of process that goes on. And that's why those nuclear reactions are so powerful and so damaging in certain cases. All right, frequency then is expressed as the waves that pass per second, and its units are one of 3. So it can be 1/seconds, which is the same if you know inverse. Some of you know inverse. already from math class. Some of you don't. If you don't, just think of it as 1/seconds. Or if you've ever heard of hertz, that's the, and I'm not talking about the car rental company. I'm talking about like the term hertz. Like sometimes they'll talk about different things being transmitted in like megahertz. Okay. Wavelength then is the shortest distance between 2 points on a wave, and it's measured in terms of length, which makes sense that it would be measured in meters. And this has to be measured in meters. If it's not, it has to be converted because you are using this guy, and if you want your units to cancel, it has to be in meters. Likewise, your frequency has to be in 1/seconds to get it to cancel. So if it's not in 1/seconds, you've got to change that as well. And we'll get into that next week. All right, so we've got wavelength. Wavelength is from crest to crest, or it could be from trough to trough. So the top part of a wave is called a crest. The bottom part is called a trough. So you can think of like an animal eating in a trough. Okay. This center line is called the origin. The distance between the origin then and the crest is called the amplitude. And so you might be familiar with different types of radio waves. One of them is called FM. And what they do for an FM is they will change the frequency of that wave, but they're going to transmit it at the same amplitude. So that FM stands for frequency modulation. So they're changing the frequency of the wave. AM then, they're going to transmit all of those at the same frequency, but they're going to change the amplitude of that wave. So AM stands for amplitude modulation. It's just how they change it up. And then when you have a radio and you've got it set on AM, you are tuning it in for a specific amplitude of that wave. If you have frequency or FM, then like I said, the amplitude is the same. It's the frequency. So you are tuning it in for a specific frequency. And radios only for communications, the radios that send out, when you tune it in on your car, they have a set frequency that they can go between, like 88 up to 107.9 or something. Okay. And that's all that the Federal Communications will allow them to have. Anything above that is for other things, and anything below that is for other things. The radios that the police use here in town, those use radio waves, and they have a set place that is goes to. And you can get for certain bandwidths on there, you can actually get a scanner and you can like follow their broadcasts that they're going across. They do have special ones that you can't hear. And they'll say switch over to channel whatever, and those people will switch it over. We have radios within our buildings. You've seen people walk around with walkie-talkies here, and they have two different things. So they've got one that'll broadcast out to any staff member, and then the admin have their own special ones that have a special band that they can switch to if there's something crazy going on that they don't want everybody to. Because I mean, if I have one sitting on my desk and you guys are in class, they don't want to hear so and so just blah blah blah, and or go and find this, whatever. So they don't want those names getting out, and they'll talk in code, like BW just went to blah blah blah, and so they'll talk in code, like you guys can't figure that out. Yeah. He went to the cafeteria to get breakfast. There you go. How's that sound? Psychic. All right. So, like I said, inverse relationship. If we have a shorter wavelength, we're going to have a higher frequency, and a longer wavelength is going to give a higher or lower frequency. So that's just kind of the same thing. Light then can be referred to as white light. It actually contains all those different frequencies of visible light. You can use a spectrum to break those apart and emit just a small part of that. And essentially what you have when things are different colors is with that white light, what's happening is it's hitting this paper, and this paper is absorbing all of that light except for, in this case, I'm going to call this green, and that's getting reflected back. Okay, and different dyes have that different ability. So this is reflecting back everything, you know, it's absorbing everything but blue. And that's why they tell you, like, if you're going out to, you know, something and you don't want to be too hot and you're going to be outside a lot, don't wear black, because black is going to absorb all of that sun energy, heat, everything. Okay. White will reflect it all back. And so you won't tend to be as hot outside if you're out in the sun and everything if you're wearing white. Yeah.
We don't have these notes in our packet.
Okay. Well, I'm still going to go through them and just listen. I think it's interesting, don't you? Mm-hmm. All right. So back to that spectrum. We're going to talk about Planck's constant next week, and we'll get into some of that mathy stuff. Photoelectric effect causes those things to bounce off, and we'll talk about the energy, and that takes us to all the mathy stuff. So yeah, anyway, I find it interesting. So